Hello, welcome to Science Chomp. Today we're going to be talking about electrical circuits. Now, first of all, before we get into the nitty-gritty, we need to have a little bit of story time. So I'm going to draw a road, and this road is a singular road which goes round in a circle like that. Well, in this case, a square. And on this road, you have a petrol station. Let's just draw a little petrol station like that. It's a bad drawing, but you get the idea. And of course, where does petrol go into? Well, it goes into a car. So I'm going to draw a little car over here. In fact, let me just draw two cars. Okay, like that. And then, so what's basically happening is the petrol goes into the cars, and the cars go around the road and back to the petrol station. Okay, but along the way, what we have is a bridge. And on this bridge, you have a man. And this man has one job to do, and that's to count the number of cars that goes past his bridge every second. Brilliant. That's nice and easy. Okay? Anyway, when the cars go past, they eventually get to this point where you have an oil drum over here. So when one of the cars comes up, okay, the man gets out, there's another man, and he measures the amount of fuel that's in the car. And then the dude in the car, what he does is he burns all of the petrol. Okay? He gets back into his car over here. He's left just enough to get back all the way to the petrol station. But before he sets off on this journey, this guy, he measures the petrol again. And what he finds is all of the petrol that's put in the car over here is burnt over here. But like I said, he leaves just enough to get back home, like a little squirt to get back home. Okay, now why am I telling you this story? Well, it's because it relates to electrical circuits. So let's think about how exactly everything relates. Okay, so what does the petrol station itself represent? The petrol station, let me just draw it like this, represents the power supply like a cell. Okay? So this provides all of the energy for the cars to go around. What does the car itself represent? Remember, we've got two cars over here. Well, the cars themselves, they represent electrons, but not a random number of electrons. This is something that we call a coulomb of electrons. Now, in case you don't know what a coulomb is 6.24 times 10 to the 18 electrons. That's a lot of electrons. The petrol itself represents the voltage. Okay? So the way we would define voltage is that it's the amount of energy needed to move 1 coulomb of electricity through a circuit. Okay? So the petrol is the energy that drives the current, basically. Which leads us on to current. Well, what is current? This man here, he measures current, and the current is the rate of flow of electrons. Or in this case, in this scenario, it's the number of cars that goes past this bridge every second. Okay? So we'll write this over here. Current is, I'm going to put like number of cars. Cars going past the bridge every second. Remember, in reality, current is the rate of flow of electrons. So it's basically the number of cars going past. Each one of these represents a coulomb of electrons. So it's the amount of coulombs going past every second. Which leads us to what's going on down here. So what's happening is the guy is using up all of his petrol. And this man here, he's measuring the petrol before and after. So the petrol difference, okay, aka PD, which conveniently stands for potential difference. Oh, I'm running out of space here. There we are, potential difference. This is the amount of energy used up by the device, and this device happens to be, in this case, a light bulb. Let me just write it here. Obviously. So what does the light bulb do? It converts electrical energy into light energy and heat energy, which is what this oil drum is doing over here. Okay? And then that leaves these two guys. This guy represents an ammeter. An ammeter is a device that measures current. And this person here represents a voltmeter, which is a device that measures the difference in voltage across a device, otherwise known as the potential difference. Okay? And this is why whenever you connect up voltmeters, it's always in parallel, because you need to measure here and you need to measure over here. So it will be a little bit like this, you see what I mean? Even though this is like what we would call a series circuit, as in one loop. Okay? So I hope that makes sense. Let me just go over it one more time. So there's a car over here, there's two cars. This represents 2 coulombs of electricity. 1 coulomb is 6.24 times 10 to the 18 electrons. That's a big, big number, okay? So they fill up with energy from the cell, and they go around the circuit. When they go past this bridge, this guy here, he counts the number of cars that goes past this bridge. This represents the current, okay? And he's acting as an ammeter. Okay, so the current is the rate of flow of electrons. When it gets to here, they unload all of their petrol, both cars unload all of their petrol from the power supply, the petrol station, to burn it as light energy and heat energy. And this person here measures the amount of petrol before and the amount of petrol afterwards, and it always ends up being the same amount of petrol that they put into the car in the first place, and then the whole thing just keeps going round and round and round. So here's another scenario. What would happen, instead of having one oil drum, what would happen if there was 2 oil drums? Well, these guys, they would know that instead of using all of the fuel to light up one, they need to save some for this one as well. So what ends up happening is they burn half of the fuel here and half of the fuel here. And as you can see, the flame is no way near as big as the one over here because they've got less fuel going through each oil drum. Do you see what I mean? So what would happen in a circuit is the voltage, which is basically the petrol. So that's right here. Petrol equals voltage, in case you've forgotten. The voltage is divided across how many different devices that you have. Okay, that's a very important concept. I've got one more scenario over here which I'd like to go over. Okay, now this represents a parallel circuit. Before, we were looking at series circuits. So series circuits have one loop. That one's got one loop with 2 oil drums. This one has one loop with 1 oil drum. Okay, so we're going to now look at what happens when we've got a parallel circuit, which looks a little bit like this. Again, I'm using the car analogy, so I'm hoping that you're keeping up a little bit. So first up, both of these cars, they fill up with petrol and they go past this bridge, and this guy counts 2 cars. Now, instead of writing 2 cars, I'm going to put 2 amps, because amps is the unit of current, okay? Now, as it goes past this point, basically the road divides into 2, okay? So one car goes across over here, and one car is going across over there. Now, both cars, the dude gets out of the car and he burns all of the petrol that he got from up over here from the petrol station, okay? And because he's burning all of the petrol, it's gonna be the same brightness as this, because what's happening is this guy is giving all the petrol, and then the next guy comes along and they give all the petrol as well, and you get like a nice big flame. And this is what's happening over here. It uses all of the petrol and it burns it, and same with this car over here. However, when they go past this bridge over here, this guy only counts 1 car, and this guy again counts 1 car. So 1 amp over here, 1 amp over here. And then when the roads join, you have 2 cars going past up here. And so you'd say that's 2 amps. So here, what we would say is the current splits up in a parallel circuit, but each component gets the full voltage of the cell. Okay, so let's have a look at an online simulation, just so that it makes a little bit more sense. Okay, so here we are with the FET Colorado circuit construction kit. So let's have a look at what's going on. I've recreated the 3 circuits that I was using earlier. And it's very easy to use. You just drag and drop your components, and you can get rid of them like this. You click that to get rid of these things. Okay, but anyway, let's just talk about current and voltage. First up, current. Now, as I said before, current is the rate of flow of electrons. And as you can see in this series circuit here, just moving it around, all of the electrons are flowing at a uniform speed. So that means that it's not getting any faster or any slower. It's about the same speed all the way through. And that means the current ought to be the same all of the way through. And they've got this little thingy bob over here. And you can test the current, and it shows it's 0.9 amps the whole way through. So that tells us the first thing about series circuits is that the current is going to be constant all the way through. But what about the voltage? Now you get this voltage thing. You make sure that the red is on the plus side of the battery and the black is on the negative side. And it tells you, let's just move it out of the way slightly of the wires. It tells you it's 9 volts, okay? Then you connect it across the bulb like that. And again, it's 9 volts. So the bulb has basically taken up all of the energy from the cell. So what it does, it takes all of that electrical energy and it converts it into light and heat. Nice and easy, okay? Now you may be thinking, what would happen if there was no bulb? And this would happen. Basically, you end up with a short circuit. And what a short circuit is a circuit with basically very little resistance. And that happens. The electrons just whiz around like mad, and you cause fire. Okay, so bear that in mind. Have a little play with this website. It's very useful. Anyway, now we've got this circuit. So bear in mind the current over here was 0.9 amps. Here you've got the same cell, and instead of 1 bulb, we've got 2 bulbs, okay? And you can visually see that the current is a little bit slower. It's 0.45, and 0.45 all the way through. Now, why is that? Well, the reason is, if you have 2 bulbs, you've got twice the resistance as that one, Okay, so all of these devices, they provide something called resistance, which slows the current down. Okay, so this circuit has more resistance than this one. Okay, let's just put this away and let's measure the voltage. Okay, so before, let's just make sure that it's the same cell with the same voltage, and it should be 9 volts. As you can see, it's 9 volts. Now, let's just see how many volts across each bulb. Okay, it's 4.5 volts on this one, and 4.5 volts on that one. So each bulb is basically taking half of the voltage of the cell. That's quite interesting, isn't it? So that's why they call a series circuit a voltage divider. Okay, let's have a look at what's going on over here. Same kind of thing. We've got the same cell, should be a 9-volt cell like this. Now, do you remember I said before in that diagram that each car gives its full petrol to each of these things? So it should be 9 volts on this one, and let's get this connected properly, 9 volts on that one. Okay, so each pathway on a parallel circuit gets the full voltage. Let's put this away. What about the current? Now you can visually see the electrons, they're moving faster here than they are over here. Okay, faster here than they are over here. So you've got here 1.8 amps of current, and then over. Alright, apologies, my video timed out, so it looks a little bit different, but anyway, I set it up again. Like I said, you had 1.8 amps of current over here, and down here you got 0.9, 0.9, and then it goes back to 1.8 over here. So the current splits by however many pathways that you have. Okay? Now, the other thing I want to show you is what would happen if we had 2 bulbs across one of these pathways instead of one. So let's make a cut over here. Let's get another bulb, another piece of wire, like that. Okay, now immediately you can see that these bulbs aren't anywhere near as bright as that. So theoretically what's happening is half of the voltage is going here, half of the voltage is going there, whereas this one is getting the full voltage. And we can test this using this one. So theoretically each one should have 4.5 volts, which it does. But across both bulbs, so let's just see this one as well, 4.5, but across both bulbs it will be 9 volts. And it's the same situation that's happening over here, where in the series circuit each one is having half the voltage, but across both bulbs you have the full 9 volts. Okay, and that's it. It's as simple as that. I hope it makes sense to you. Just be a little bit careful, know the difference between a series and a parallel circuit, and know what happens with the voltage and the current. Thank you very much for watching, and goodbye.